Hi everybody. Today I'll discuss the implementation of the closed form solution of the 1.5 PN binary black hole system, which has got both components spinning and it has got arbitrary eccentricity, arbitrary masses, and yeah, arbitrary spins. So I'm talking about a system which is described by the 1.5 PN Hamiltonian system, right? So that's the Newtonian Hamiltonian. This is the 1 PN Hamiltonian. This is the 1.5 PN Hamiltonian. Let's ignore the 2PN part. And don't worry about the web links. I'll provide all the web links, all the URLs which I discuss in this video in the video description below. Okay. Okay. All right. So let's go over the background. The the solution for this 1.5 PN system, let me hide the 2PN part. The solution for this system was first given in this paper. Okay. Um, and let's call it the standard or the more straightforward way of computing the solution. Okay, that's what we'll refer to. Uh, we'll refer to this method of computing as the standard way for this video. And then, so this came out in 2019, and then later, these two papers, this paper and this paper, they gave the action angles way of computing the solution later in 2020 or 2021. So we'll be implementing these two methods of computing the solution in our Mathematica package. Um, so what are the pros and cons of these two methods? Well, as the name suggests, the first method, the standard way, is shorter as compared to the other. It's more straightforward. And the second one is lengthier, but this action angles way, the lengthier method of computing this solution, this is amenable to getting extended to 2 PN. Okay, so if you want to extend the 1.5 PN solution to 2 PN, the first method is not so easy. It looks, difficult, very difficult to almost impossible to extend this solution method to 2 PN. But this one, the action angles uh, way it can be extended probably, hopefully, as of now. Okay, and to for a more pedagogical exposition of these solution methods, there is this set of lecture notes on GitHub. Okay, and a copy of this has also been put on archive. Now, why is that? Because this has been done because if you want the most updated version of these lecture notes, you can look at GitHub. That's what will be more frequently updated. But if you want to cite these lecture notes, you can use the archive version to cite these lecture notes. Okay, now let's head over to the real deal, the Mathematica package, which implements these solutions. So here's a Git repo which has this Mathematica package, BBH-PN-Toolkit. That's what it's called. How do we install it? Okay, so let's see. You can click this link, this master.zip link. If you click on this link, this zip file will get downloaded over here on your computer. Now let's extract it. So I get this folder upon extraction. Okay. Now all you have to do is copy and paste this folder in the relevant Mathematica directory of your computer. And this relevant Mathematica directory has been mentioned on the README file of this Git repo. For Linux, it's this. For Mac OS, it's you've got these two paths, and for Windows, it's this. So you just copy and paste this folder in these paths, whatever is relevant to you. Okay. Now this means your package is installed once you have copied and pasted. So let's run the package. So we have provided a sample uh, package running notebook in this folder. So here is the run package.nb. That's the Mathematica notebook using which you can run the package. So let me open this. Okay, so what does this Mathematica notebook do? Well, it does a couple of things. Or what does this package do, rather? So it can compute the frequencies of the system, all the five frequencies of the system. When I say frequency, I'm talking about frequencies in the action angle framework. Okay, So with an action angle framework, frequencies are the rates of change of the angle variables. That's what frequencies are. It can compute all the five frequencies. It can compute uh, it can implement the two solutions, the standard way and the action angles way. It can also do the numerical integration because you may want to compare. So you've got these, there are two closed form solutions. How do these match? How well do these two match with respect to the numerical solution? So it can compute the numerical solution too. And just as an addendum, we also provide a notebook which can compute the Poisson bracket between any two general quantities. So why do we do that? It is because to compute these closed form solutions, a very important quantity which is used over and over again is the Poisson bracket between any two general quantities. So we just give a Mathematica notebook over here which can compute the Poisson bracket between any two general quantities. So let's check them out one by one. Okay, so I'll open this notebook, run package. Okay, so this line basically loads the package. Okay, once you have copied and pasted that folder in the relevant directory, now you can load the package. And here is where you enter the parameters of the system. Okay, okay, so M1 has to be the bigger mass. M2 has to be the smaller mass. That's how you enter the parameters, M1 and M2. These are the two masses of the black hole. TF is the final time at which you want the solution. Okay, epsilon is 1 upon c squared. C is the speed of light. And I've set epsilon equals 1 upon 1000. So you can clearly tell I'm not following the SI units because 1 upon epsilon, where epsilon is 1 upon c squared, is not equal to 1 upon 1000 in SI units. It is some weird set of units. And of course, the masses of black holes in SI units is not this. But anyway, this is just for illustration purposes. So now I enter the initial position vector, the initial momentum vector, and then I enter the initial spins. Okay, so just a heads up, the spins, the spin angular momenta is not given by just this vector or just this vector. This vector times the square root of epsilon is all of this in entirety is the spin angular momenta of the first black hole, and so on for the second black hole. Okay. The reason I put this additional square root of epsilon is that in the post-Newtonian approximation, spins are much smaller than the orbital angular momentum. Okay, the orbital angular momentum is r cross p, cross product between r and p. So spins are much smaller than that, than r cross p. And to make them smaller, by hand I'm enforcing this thing like square root of epsilon. I'm multiplying it by that. So this thing um, combined together is the spin angular moment of the first black hole, and same way for the second black hole. Okay, so I have run this cell. Now let's get the frequencies. So this command will get you the frequencies. Frequency is a function, and this frequency and its second get its second element that will be returned into freak array, freak array, and this is basically these are the four frequencies. So one of them will always be zero. So effectively, you have only four frequencies, not five. Okay. Now let's get the solutions. So the first line gives you the numerical solution got by numerical integration, which is basically meant for comparison purposes. The second line gives you the action angle solution. The third line gives you the more straightforward standard way of computing the solution. So yeah, although the authors which proposed this solution, the standard way, uh, they dropped the 1PN part, but in our Mathematica notebook, in our implementation, we have redone their calculations and we have included the 1PN part. We did not drop anything. So yeah, it's 1PN, 1.5PN complete. So I'll just run this again, run this cell. And yeah, if you want to I don't know why it is complaining, so I'll just quit it. and run this entire notebook all over again. Okay, the complaint I think goes away. Okay, so yeah, you can see there is agreement between these two solutions. This is the first array is the R vector at t equals tf. This is the P vector at t equals tf. This is the S1 vector at t equals tf. This is S2 vector at t equals tf. Okay, so there is agreement, and this basically shows you the solution at a single point of time. To get a more holistic picture, let's look at some plots. So we have done these plots not exactly for this system, but a slightly different system. Um, yeah. So this is where we show the x component of the position vector um, at some later time. So you can see this plot is not from t equals 0. It's not starting from the initial time. It's much, much farther away, actually. So it's at t equals 3050 to 3200. You can see like the time it takes for one cycle is around 50 units of time. So it has completed many, many cycles when it gets to this point. T equals 0 is further towards the left, like it's like beyond what this figure can capture basically. So it's much later towards the much farther down the line. Actually, it's not in the initial stages of the evolution, and even at this time the agreement is kind of good. So you can see there are two distinct things over here. Like I can see there are two distinct plots. So what's happening here is that the two closed form solutions, action angles and the standard way, they agree very well. You can't really distinguish them visually. But these two closed form solutions, they differ by some amount from the numerical flow. So what you can distinguish visually is the distinction between the numerical and the two closed form ones. Okay, the two closed form solutions, these two cannot be distinguished visually, and that is what is happening over here. This distinction between red and blue, what you can see over here, is between the numerical and the other two. Okay, now let's look at the orbital angular momentum z component, and this one is being shown from the initial time t equals 0 to 3000. So you can see, at least in this figure, we can't distinguish those three solutions. They just overlap very well. And let me try to zoom in further. I'll try to zoom in into this area, like beyond 3000, a small time interval beyond 3000, which will be done in this plot. Okay, so beyond 3000, which is like 3050 to 3200, you can see that I can see some distinction if I zoom in very closely. So this is the distinction between numerical and the other two. It still cannot resolve the other two, action angles and the standard. So yeah, there is agreement. We'll go with that. And this is the x component of the spin vector starting from initial time t equals 0 to 3200. Uh, oh no, not t equals 0, but later stages like around 3000 to 3200. And all of these three kind of agree. Same with spin 2. Anyway, so we have seen that they agree, right? Okay. Now, right now, this Mathematica package, it's very slow, and in the coming weeks and months, we'll continue to improve the speed and keep fixing the typos if we find any. Now we can talk about, yeah, I can show you how to compute the Poisson bracket. Okay. So to compute the Poisson bracket, we'll go back into this folder again, and this time we'll pick this notebook, Poisson bracket notebook. Let me open it. Okay, now this Poisson bracket notebook, it relies on X tensor, or rather X act, right? So the thing is, first of all, you have to install this X act Mathematica package, which you can find. in this its documentation is available online. So I'm assuming that you have installed Exact in your computer, this Mathematica package, and it's also done in a similar way. I think there is a folder which has to be copied and pasted in the relevant Mathematica directory. Please read this documentation. So once you have installed Exact, now you open this um, notebook. And yes, to run this notebook, you don't have to install our BBH-PN-Toolkit. You don't need that. To run this Poisson bracket notebook, you only need to install the Exact or Extensor uh, Mathematica package. Okay, so this is all a bunch of text which you don't need to worry about. Just we can go further down. I have coded the Hamiltonian, Newtonian 1pn, 2pn and all, but that's unnecessary. Okay, so here are some quantities between which I would want to compute the Poisson bracket. There is var1, var2, var3, var4. So the way it goes is that this L is the orbital angular momentum. I have defined this, I think, earlier over here. L is like a cross product between R and P. So there is epsilon tensor times RP. That's the cross product of R and P. That's the orbital angular momentum. This is the R vector. This is the P vector. And this uh, alphabet inside the square brackets is basically, it's like an index. So LA is like L Li, or you can call it LA. It's like the index. So LA basically represents the L vector. RA is like, R superscript A. It's the R vector. Yeah. So this is S1, the first spin. If there is a 1 in the square brackets following S, that means this is spin 1, and this becomes spin 2. So this is basically spin 1's bth it's like spin 1 upper index B, L lower index B. So lower indices are denoted by minus sign. So if I do L of minus A, it becomes L lower index A. It becomes this. That's how it is to be interpreted. So you have got spin 1 upper index and L lower index. So it becomes the dot product of spin 1 and L. So it becomes S1 dot L. That's what this represents. That's what var1 is. So that's how we input. That's the convention of extensor. Okay, now these three lines give you the Poisson bracket between var1 and var2, var1 and var3, var3 and var4. So let me run the entire notebook and we'll see. First, I'll quit the kernel, just clear everything up. So Control A selects all the cells in the notebook and then I hit Shift plus Enter. The notebook runs. Okay, so here's my output basically. The first Poisson bracket turns out to be this. So that's a dot product. P dot S1, R dot S1. It is to be multiplied with R vector. This is to be multiplied with P vector, and this entire thing is the output. Okay. Here in the second line, this second Poisson bracket becomes epsilon tensor times R times S1. So this basically is R vector cross S1 vector. All right. And let's look at var3, var4. You can see var3, var4 is basically uh, this is a position, this is a momentum, and between them, the Poisson bracket, as you might know, is Kronecker delta, or zero, or either 0 or 1. So that's exactly what it is. It all works out. So yeah, that was basically the description of all the things this Mathematica notebook, Mathematica package, BBH-PN-Toolkit can do for you. Okay. Just to refresh the memory, it can compute all the frequencies, it can compute the numerical solution, the action angle solution, the standard solution, and we have got this uh, Poisson bracket notebook which can compute the Poisson brackets between any two general quantity. Okay, so that's all for now. See you later. Bye bye.